Good day, everyone. So in today's class, we'll be looking at speed and acceleration in simple harmonic motion. At the end of the lesson, we'll be able to define speed and acceleration in simple harmonic motion. We're going to learn the formulas and also how to use the formula solving problem involving simple harmonic motion. So let's dive into this. So we're going to start with exactly what simple harmonic motion is. In short form, we call it SHM. In simple harmonic motion, an object oscillates back and forth or to and fro around the central equilibrium position. And when this is happening, both speed and acceleration change continuously, okay, throughout the motion. Now, what really happen when this is happening? Now, during simple harmonic motion, please take note that even though we have speed and acceleration involved, speed remain constant while acceleration continue to change. Okay, and when we say acceleration is changing, what we are saying is only the magnitude part of acceleration is changing. Is constant. The direction part is changing. Only the magnitude is constant while the direction is changing. Okay, so simple harmonic motion is a motion that involves the to and fro movement of an object, okay, around the central equilibrium. A good example of this is the motion of simple pendulum. Okay, when you see a simple pendulum moving, what you will notice is this. Let us say that this is a ceiling or a suspender where the string of the simple pendulum is um, hung, okay, and then this is now the board. Now, when you display the simple pendulum this direction, what you notice is that it moves, begin to move and go to the light extreme. Okay, let's put it like this. Okay, so this is the equilibrium position because this is called equilibrium position because this is the point where it will eventually stop and stay. Okay, so as it's moving like that to and fro, okay, it's moving with the speed, okay, it moves with the speed v and acceleration a. Now the speed is moving with is constant, but the acceleration is changing. So take note of that. So that is the concept behind simple harmonic motion. Now, what do we observe in the speed? In the simple harmonic motion, we say that in the speed part, speed is maximum, the speed is maximum at the equilibrium position, like I drew earlier for that of simple pendulum. Now this is the equilibrium position, and these are the extreme end of it, right? Now at this point, we have maximum speed here, okay? While at the extreme part, we have minimum speed. We have minimum speed. We have minimum speed here. We also have minimum speed here. So speed is zero at the extreme, while it is maximum at the equilibrium part. Okay, so take note of those key behavior of speed in simple harmonic motion. And the formula we can also use for simple harmonic motion is this. Okay, we use V to represent speed. Sometimes we use velocity interchangeably with speed in this topic. So when you see V, just know that it could be velocity, it could also be speed. And not just speed, we call it linear speed. So linear speed equals amplitude multiplied by angular speed then cos theta. So take note of that. That this formula here is the formula that link speed and angular speed, linear speed and angular speed together. All right, linear speed and angular speed together. Right. So these are the concepts you should know in speed for simple harmonic motion. Now, angular speed in the first slide, they are related with linear speed like this. Aside from that, another relationship is this. Linear speed is related with angular speed with this formula. V equals to R multiplied by angular speed. Okay, why some write it this way? But it's still the same thing. Alright. So angular speed is measured in rad per seconds, while radius is measured in meters. Okay, so take note of this relationship between linear speed and angular speed. Now for acceleration, what are the key behavior in acceleration? In acceleration, at the equilibrium position, acceleration is zero. It's the opposite of speed. For speed, at equilibrium position, speed is at maximum, but for acceleration, it is at zero. Okay? While at the extreme part of it, acceleration is at the maximum, while speed is at zero. And acceleration is always directed towards the equilibrium. Okay? So, drawing it again, drawing the diagram of a simple pendulum as an example, when you have a bulb in the equilibrium position like this, and at the extreme end, it moves this way. Now, at this equilibrium position, the acceleration is always directed towards there. That's the mission of acceleration. It's always directed towards the equilibrium position. And that's why in the formula you have it to be A equals to capital A omega sine theta, where the A there represents the amplitude. Now the omega represents the angular speed. The negative sign there shows that the acceleration is moving towards the equilibrium part. So in case you are asked what does it indicate, the negative part indicates acceleration point towards the equilibrium position. Okay. Now bringing acceleration together also. Acceleration can be two. We have linear acceleration and angular acceleration. Just like we have linear speed and angular speed. For linear speed, we know linear speed is related to angular speed with this formula, where the v there is linear speed, w the angular speed. For acceleration, a represents the linear acceleration, while alpha represents the angular acceleration. So by formula, linear acceleration equals to angular acceleration times r, just like this. So they're just the same thing. Just remove angular speed and put angular acceleration here. Remove angular linear speed and put linear acceleration here. So this is the way to relate them. Linear speed equal to the product of angular speed times radius. Linear acceleration is equal to product of angular acceleration times radius. So take note of these formulas that we use in solving problem. Now let us see one or two questions here. Here it says, if a freely suspended object is pulled to one side and released, just like that of a circle pendulum, it oscillates about the point of suspension because the acceleration is directly proportional to the displacement. Yes, acceleration is always proportional to displacement. Take note of that. In simple harmonic motion, take note that acceleration, which is A, is proportional to displacement, which is Y. So by formula also, you can say A equals to minus omega square Y. So they are proportional to each other. So A is correct. B, motion is directed away from the equilibrium point. No. Motion in simple harmonic motion is always directed towards the equilibrium point, not away. C, acceleration is directly proportional to the square of the displacement. No, it's not to the square. It's actually to the square of the angular speed. Velocity is minimum at the equilibrium. No, velocity is maximum at the equilibrium position, like we said before. It is acceleration that is minimum at the equilibrium point. So the correct option is A. Another question here says, an object moves with uniform speed round a circle. Okay, its acceleration has a constant magnitude and constant direction. No, it is the magnitude that is constant. Direction of the acceleration is not constant, so A is wrong. Constant magnitude and varying direction, yes, B is correct. C, varying magnitude and constant direction, no. The magnitude is always constant, and that's because the speed is constant. But another formula for linear acceleration is v squared over r. So this v, which is speed, is always constant. That's why the magnitude of acceleration is also constant, but the direction is varying. So the correct option is B, constant magnitude and varying direction. C is varying magnitude. No, it does not vary. It is the direction that varies. Okay. This is varying magnitude. It does not vary. All right. So the correct option is option B, constant magnitude but varying direction. All right. So let us see another question here again. It says a gramophone a gramophone record takes 5 seconds to reach its constant angular velocity of 4 pi radian per second from rest. Find, this is from, please take note, it's from, not from. Find its constant angular acceleration. Okay, now A gramophone record takes 5 seconds. So we are giving T. T here is 5 seconds. Okay, T is 5 seconds. To reach its constant angular velocity, whenever you hear angular velocity, you know it's omega, that's W, of 4 pi rad per second. The unit of angular velocity is rad per second, right? Okay. Find its constant angular acceleration. You know, angular acceleration is alpha. Okay. Remember that linear acceleration is equal to angular acceleration times radius. Okay. Now, to find alpha, so how do we find this? Remember that from rest means that the the initial angular speed, that's omega 1 is 0. Anything from rest means 0. While the final one, which is omega 2, is this. So remember, formula for acceleration is usually change in velocity over time. The same thing for angular acceleration too. Angular acceleration will be change in angular velocity over time. So this is another formula again, which is W2 minus W1 over time. And here our W2 is 4 pi minus our W1 is 0 over T. T is 5, right? So finally 4 pi minus 0 is still 4 pi over 5. So the correct answer is 4 pi over 5. But 4 pi over 5, we need to stick simplify further. So 4 over 5 means 0.8, right? 0.8 then pi. So it's 0.8 pi meter per second. Okay? That's the solution to question 24. 0.8 pi radian per second. Alright, let's see another question here. It said, from the diagram beside here, this time around, the bulb of the pendulum bulb has the fastest speed at, okay, we have said it before. So this is the equilibrium position here at x. The speed of velocity at the equilibrium position is always maximum. So this is where we have the fastest speed here. At z and at w, the speed will be very, very low. Okay, it is acceleration that is at minimum at the equilibrium position. So let us check option A, W. No, we are looking at the fastest speed, which is maximum speed. So W is wrong. B, Z. Z is wrong. This is at the minimum part. Y is wrong. Nothing between. X is the correct one. At the equilibrium position, speed is at its maximum. Y acceleration is at its minimum. So take note of that too. Now let's consider the last question. He said, if a wheel 1.2 meters in diameter rotate at 1 revolution per second, calculate the velocity of the wheel. Okay, now if a wheel 1.2 meter diameter, so the diameter here is given to be 1.2 meters, but we don't have diameter as our parameters in this topic, so we have to change it to radius. Remember that radius and diameter, they are related, so radius is equal to diameter over 2. Take note of that. So our diameter is 1.2 then over 2. So our radius there will now be 0.6 meters, right? So rotate at 1 revolution per second. 1 revolution per second means that is angular speed. So angular speed by formula is also 2 pi n over t, right? That's another formula for angular speed that we learned in our last class. So, and that will be equal to 2 times pi means 22 over 7, or approximately 3.142 to 3.14 times n means number of revolution. Here we are told is 1, so it's 1 over per second means 1 second, so over 1, 2, this is 1. So from here now, multiplying 2 by 3.142, let me do that. 2 times 3.142, so that will give us 6.284. So we have this of it 6.284 rad per second. That is our omega now, our angular speed. But we have to calculate the velocity of the wave. So how do you calculate the velocity of the wave? Remember that whenever you have to calculate velocity, now you are calculating linear velocity or linear speed. If it is angular velocity to be specified, just like it was, just like we obtained this one now. So but once it was just called velocity, know that it is referring to linear velocity or linear speed. So in that case, we know that linear speed is v equals to angular speed times radius. So we have obtained our angular speed to be 6.284. So 6.284 multiplied by our radius, which is 0.6. 0.6. So let's calculate that. So 6.284 times 0.6, so times 0.6, that's giving us 3.77. Okay, so we have it to be equal to 3.77. Okay, and since you are dealing with linear speed, you need to be meter per second or meter slash s. So 3.77 approximately will be 3.8. Option A is 3.6, no. Option B is 3.8 meter per second. That's correct. Approximately to one decimal place. That's 3 point. That's correct option. No option C is no option D. All right. I hope you have been able to learn something in this class. You'll be able to see how to apply a formula for acceleration and speed in simple harmonic motion. Thank you for watching and have a wonderful day. Bye for now.